Section 6.1.33-T. The probability distribution of the random variable x represents the number of hits a baseball player obtained in a game for the 2012 baseball season. So here we have x, which is equal to 0, 1, 2, 3, 4, 5, and there are the probabilities for each one. Now, the probability distribution was used along with statistical software to simulate 25 repetitions of the experiment, which is 25 games. The number of hits was recorded. Approximate the mean and standard deviation of the random variable x based on the simulation. The simulation was repeated by performing 50 repetitions of the experiment. We're going to approximate the mean and the standard deviation of the random variable. Compare your results to the theoretical mean and standard deviation and what property is being illustrated. So, the first thing we want to do is we want to compute the theoretical mean of the random variable x for the given probability distribution. So we're looking at this table up here. We want to be able to find what is the theoretical mean for that data set. So we're going to open up this table in StatCrunch. So we're going to go ahead and then here's the data table. We're going to go ahead and open that up in StatCrunch. Okay, so you can see here that in our first column is x, and this is the probability column. And again, we want to determine what is the theoretical mean and what is the standard deviation. So we're going to go to Stat, select Calculators. We're going to scroll all the way down to Custom. The values in is going to be x. The weights in are going to be p of x. And then we're going to compute. So down here we can see that the mean, which is 1.7125. So let's go ahead and write that in there. So we know that the mean is equal to 1.7125. And they want us to round that to the nearest, or to 3 decimals. So that's going to be 1.713, and that represents hits. Okay, now what we want to do is we want to compute the theoretical standard deviation, which we already have found here. And there's the standard deviation. It's 1.2829044. Okay, and again, we want to round this to 3 decimal places, so we can see that the standard deviation is going to be 1.283, and that represents hits. Okay, so now we want to approximate the mean of the random variable x based on the simulation for 25 games, and we also want to approximate the standard deviation of the random variable x based on a simulation for 35 games. So what we're going to do is, we're now going to have to open up a new box for the data set. So we're going to now go to the data set that represents, here we click on the icon, so we have 2 sets. We have the table of numbers hits for 25 games, and there's one for 50. So we're going to open up in StatCrunch the table for 25. And what we want to do is we want to approximate the mean and the standard deviation. So this is all in column number 1. So we're going to go ahead and hit Stat, and then we're going to go to Summary Stats, and we're going to select columns. So we're going to select variable column 1. We want the mean, and we want the standard deviation. So let's go ahead and compute that. So I'm going to go ahead and copy that. Okay, and so now what we want to do is we want to be able to then determine, okay, what is the mean? So the mean, or the approximate mean, is 1.680, and that's 1.680 hits, and we're rounding out to 3 decimal places. So again, that's based on the simulation for 25 games. And then what is the standard deviation for the 25 games? Well, again, we're going to round that to 3 decimal places. So we can see that the standard deviation is going to be approximately 1.215 hits. So now the next question is we want to do the same thing, but now we're going to use the simulation for the 50 games. So we're going to come back up here. We're going to again now open up the new data set, which is the one for the number of hits for 50 games, and we're going to open that up in StatCrunch. Again, we're looking at column 1, so we're going to hit stats, go to summary stats and select columns. We're going to select our column, and we want the mean and the standard deviation. So let's go ahead and copy that. So therefore, we determined that the mean is approximately 1.760 hits and then for the standard deviation, that is going to be approximately rounded to 3 decimal places, is 1.302 hits. So now let's summarize that. So we can say that the theoretical mean and standard deviation are 1.713 and 1.283 hits, respectively. The mean and standard deviation based on the simulation for 25 games is 1.680 hits, and the standard deviation is 1.215 hits, respectively. And the mean and the standard deviation based on a simulation for 50 games are 1.760 hits and 1.302 hits, respectively. Okay, so now the last part's asking us to then, we compared our results. It says what property is being illustrated. Okay, so first and foremost, okay, we can see that for the simulation of 25 games, the mean is about the same as the theoretical mean, and the standard deviation is about the same as the theoretical standard deviation. For the simulation for 50 games, the mean is about the same as the theoretical mean, and the standard deviation is about the same as the theoretical standard deviation. Now, going back to that last question, okay, what property? Well, first and foremost, the law of large numbers states that as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. Now, when we talked about the empirical rule states that if a distribution is roughly bell-shaped, then approximately 68% of the data will lie within 1 standard deviation of the mean, approximately 95% of the data will lie within 2 standard deviations of the mean, and approximately 99.7% of the data will lie within 3 standard deviations of the mean. Now, when we talk about Chebyshev's inequality, it states that for any data set, regardless of the shape of the distribution, at least 1 minus 1 over k squared times 100% of the observations will lie within k standard deviations of the mean, where k is any number greater than 1. So, going back to our question again, it says, what property is being illustrated? Well, the property that's being illustrated, the simulation is illustrating the law of large numbers. Because again, the law of large numbers states that as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome observed gets closer to the probability outcome. So that means that we've gone through a simulation of 25 games, and then we've increased it to 50 games.